A motion law acts to aggregate compact energy quanta in objects from nucleon to astronomical size. A repulsive effect of outward IR heat radiation, or actually radiation in any frequency range, its momentum may oppose the motion law aggregating effect. These are the two balancing things that I've been talking about. The motion law and centrifugal radiation pressure effects is an example. I work with the temperature-dependent Casimir force experiment using the Binary Mechanics Lab simulator software to show that that is temperature-dependent, okay? And temperature, when you raise it, increases the density of energy around the object. Between two objects that are both radiating, where will be the greatest energy density? Between them. So they'll be attracted to each other according to the law of motion. It's that simple. This is not a very complex idea. The lunar laser ranging study showed that the Earth-Moon gravity increased at higher lunar surface temperature facing Earth. I also analyzed the gray satellites, confirmed that gravity surface temperature dependence again. Here we have both spheres at a temperature greater than 0 Kelvin, and they're emitting radiation. So where is going to be the area of higher energy density? Between the two objects. That's why they're attracted to each other. It's not directly related to the mass of these objects. The two objects with greater quanta density than the surrounding volumes are shown. If object temperature is greater than 0 Kelvin, radiated energy will increase quanta density most at the nearest surface of the other object. Therefore, each object will tend to move toward the other. This motion will be opposed by the momentum of incoming quanta. Okay, here's the moon study where you can see that there's about 10,000 kilometers difference between top and the bottom here. And at full moon, or near full moon, is when you have the closest approximation of the two items. So that when you have the greatest energy density between the two objects, they're closer compared to 10 or 11 days from full moon when they're more distant. The law of motion is shown in this study. Galaxies tend to clump together in groups, and there are volumes between these galaxies with less number or density of galaxies in them. If we look at this figure, it gives you a law of motion perspective on that. If we have two dimensions, right, left, and foreground and background, and with the height of the mountains here depicting areas of higher energy density, the altitude of these mountains is higher quanta density. Let's take these two arrows. You notice that quanta will tend to move toward this higher density area to the upper right. And just next to it, these quanta will tend to move away from the others toward an area of higher density to the left there. And there are other examples of this phenomena. This arrow going up here and these arrows going up in the other direction, leaving areas of lower density and the aggregation effect of the law of motion. So that we can then say that, okay, here is where we have concentration of galaxies, of whole galaxies, many of them with a relatively sparse distribution of galaxies in between, and then another peak in the galaxy density here. And so that's what this figure is showing. It's showing on a cosmological scale, this law of motion makes a lot of sense. Also, we can talk about creating the surface of an object. The law of motion would tend to compact objects with outgoing radiation pressure pushing the material toward the surface of an object like a planet or the moon or whatever, or the Earth or whatever, but also with a centripetal motion here at the surface. I show four arrows, but all the way around on the surface, quanta will tend to move toward the higher density area here to form the surface, actually. And so this is, again, how the object surfaces can form again according to the motion law. And the outward heat radiation momentum, I've already talked about that. I think that's the end. Bingo, that sound means that's the end of the slides. Okay, thank you.
What exactly is meant by quanta? Is it consistent with Einstein's thought that light consists of tiny packets of energy called quanta, or is it something else? Also, why is a given particle or quanta attracted to higher energy fields? What type of energy is this? And is it known why this effect occurs?
The quanta of light, probably that Einstein was referring to, is actually composed of thousands, maybe millions of quanta at the level of binary mechanics.
Is that similar to photons, or is it something altogether different?
Well, the idea of the photon is an aggregation of perhaps millions or even billions of quanta. What was the second question, Jerry?
Why is a given particle or quanta attracted to higher energy fields?
We define a volume, which is the binary mechanics length constant cubed, and it either has something in it or it doesn't. It doesn't tell you what it is, okay? It just says if it's in the one state, it has something in it, and I'm calling that a quanta. And so if that helps answer the question, I don't know.
Well, there are different types of energy. I didn't know what type of energy the field generates, or what it's composed of exactly.
Different types of energy.
What type of energy is that present within the higher energy fields or lower energy fields?
The density of quanta would be greater in the higher energy density fields, okay, areas or volumes.
I think in the way you're using it, it's just a general concept of energy. It's not saying electromagnetic energy or gravitational energy or any particular type. It's just energy, right?
Yeah.
Does that help you, Jerry?
Yeah. By what means is the energy generated? Like what causes the energy?
That's a question beyond binary mechanics. Binary mechanics is simply telling you that it seems that space is organized in the kind of structure I showed you in the slides of the spot cube and the spot unit. So that's your organization of space, and those locations can contain either a one, something, or nothing, zero. It does not tell you what it is. Is the something a little Tesla automobile? Is it a banana? Is it a tinker toy? It doesn't tell you that. So if you want to know what a one state is, you're going beyond what binary mechanics can provide to you at the present time. We're just saying that there is one states and zero states, and therefore we can make some real stunning advances in physics.
How does mainstream people react when they hear about this? What do the mainstream people say?
Well, since the takeover of Twitter and its transformation into the X.com website,
right,
supposedly with less censorship, I've been started to post again, and oftentimes referring to like putting people's names in there so that they would get copies of my post. And so we're starting to get maybe some reaction there. Yeah. What binary mechanics needs basically is a publicist. We're not seeking funding from other agencies, and there's some things that we're doing which frankly other people wouldn't have the security clearance. That's sort of the situation we're in at the moment. And I've called out to DARPA, for example, and to other agencies. So I think they're sort of aware. And if there were a publicist in charge of this aspect of it, it would certainly help. For someone who's really interested in making a lot of money, I want to bring them on board as well, because there's money to be made here. Well, thank you for your attention. You've been very patient, everybody. I appreciate that. Thank you.